So I'm starting on a new stuff whereby I'm trying to see whether we can get a few things done in electronics, and such things that I'm talking about is there are a few things that are looked as complex from my experience in teaching electronics. There are those things that people tend to think they are so complex, and one of them is to find the current in circuits, and these couple of methods used, for example, using the Kirchhoff's, using the Thevenin's theorem, and Moulton's theorem. So I will concentrate on these two because this one is a piece of cake to most people. But if you find any problem in working with this one here, then you can write up in the comment section, and see whether we can actually go through it and make sure we highlight those things that you find are a little bit confusing to you, or which you find that they don't go well with you. So let's move it. Thevenin's theorem. And it states in a linear circuit, having a two-terminal output, load is equivalent to the voltage source, is equivalent to a voltage source in series with the load. In series with the load. This is what we saw. The keywords here are linear. Linear circuit is having linear components, resistances, inductors. Two-terminal, it is you can get negative, positive. That is the ground and positive. And then this output load is equivalent to the voltage source in series with the load. And how do we get this? We get this in a form, the circuit would look like this. So the circuit would be, we are having a voltage source. This voltage source with the network of the total of all the resistances, okay, the components we had or elements we had in our circuit, and these are the ones which will be representative of RTH And then we have this voltage source, which we call the Thevenin's voltage, and this one is our two terminal, these two terminals here, and then we get this voltage source with the load which we talk of, and we normally take it as RL. So this is here a load resistance. So this is load resistance, RL. RL is the load resistance. Okay, so we need to hustle to find that we get the Thevenin's resistance, then Thevenin's voltage, and finally we get the current. The issue would be current I here through the load. Now, a few key things. In a circuit, within a circuit where they would have told you to find the current I, that part will be the load. That resistance that they would be asking you to find the current through will be considered, is the one you are going to consider as the load. And once you consider that as the load, then you know that you are going to find out these other parts. So we are going to take a case of a nice circuit, and the circuit we shall move step by step, go slowly by slowly, and make sure that we first find the Thevenin's voltage, find the Thevenin's resistance, this one here, and then Thevenin's voltage, and the other resistance that we would have taken as the load, bring it in, and then combine the two, get the using this as a single loop, get the current from I equaling to or equals to Thevenin's voltage over the Thevenin's resistance plus the load resistance. Once we get this, then we would have solved the issue and reduced this. And this is a method that most people find a bit strange, and I can assure you from today onwards you're gonna find it very, very easy to work with. So now I'm sure you have your paper and you have your pen and your calculator probably, or most likely, and we are ready to go. We're going now to look at an example. And this example we're gonna use Thevenin's theorem to find current I4 in the circuit below. This circuit is that you have a current source and after having this current source you have a resistance R1 here, and the value of R1 is 0.8 kilo ohms, and then you have the points. So you have the other resistor R2, and then you have the resistor R4, and we are supposed to find I4 around here. This is 0.1 kilo ohms, and this is 3 kilo ohms, and then you have another resistor here, the 2 kilo ohms, and then a voltage source here. I'm gonna have to redo this part so that this can be, yes. So I'll put the resistor here. And these are 2 points A, B. So we are supposed to find this current through here. This is about 21 volts. This is the voltage is going up like this, the arrow, and then here we have the current going downwards here, and this current here is 21 milliamps. So this is our equivalent of the RL. So that means we must make sure that first of all, we shall, step one, we take it aside and isolate it out. Isolate it out. After isolating it out, then we try to first find the voltage here and also the resistance of the total circuit RTH. For voltage VTH, once we have removed this one, we need to find the voltage across A and B. That's easy, because we shall be having this voltage here being divided across this and this other resistor. So here we shall be having a potential divider, and then when we eventually, then here we get the I times R of potential, the potential drop here, which will give us, so here the PD would be moving in this direction, and then here the PD is moving in this direction. So the sum would be this here minus this one here, so that we get the value of the PD across here, and the PD across this part here is the same as the Thevenin's voltage. Too many stuff, so I will try to remove a few things. So we are isolating this resistor away so that we keep it aside as a load. So step one, I'm trying to now look for the potential across AB, which is our Thevenin's voltage, and that potential across here, the potential now which we shall get across here here. This is what we shall get as the VTH. And so a couple of things will have to come through, and these couple of things are that one, we have this section here. This section here is simply this current that will flow through here. So on this side we have 21 milliamps times the resistance, which is 0.8 kilo ohms. This is what we shall get here, and it will be flowing in this direction here, because of this arrow. And then here, this side, if you want to visualize it properly, it's like at this point C here. So we have this point C, and then we have a resistance, this resistance here of 3. So maybe I can leave it like this, but now try to bring this one, shape it like this. But I wanted us to look at it in a more nicer way, because the moment you put it in an actual shape, it becomes easy to visualize. So it ends up looking like this. This resistor can come and be here, and this becomes our point C, and then we have the 3, and then we have the voltage source here, and so this is the 21 volts. So that means we would be having the potential across here is the, okay, maybe since we know what we are finding, I can remove this so that we get a good feel of what is happening here. And this good feel of what is happening is that we shall have the, so I'm going to slide this resistance here and bring it here, so it is going to be here, and this is our point C. And then now the voltage source, just to make sure that it is well placed for easy visualization. I'm trying to do the visualization bit so that you visualize it nicely. So I have the 21 volts here, and then you have the resistance here, the 2K, 2 kilo ohms. So the PD across here, that will be across this part, which will be moving in this direction down here. It will be a direction which is opposite to this. So here we shall be having this as the one which a potential divider. So this potential divider here, this whole part here, is going to be for the potential divider. So this potential divider here will eventually give us the one which is engulfing the potential that we want is the 3, so it will be 3 over 3 plus 2, then times the 21 volts. So this is 3 over 5 times 21, and so we end up with just to be sure of what we are doing. So that is 3 over 5. 3 over 5. The space is not enough, so I'm trying to make sure that things work out easily. So we have 3 over 5 times 21. 3 over 5 times 21. And this should be equal to 12.6 volts. Here we have 21 times 0.8. This is 16, because the kilos will go a milli, and so we get 16.8 volts. This is plus, this is minus. So the VTH would be equal to 16.8 minus 12.6. This is equal to 4.2 volts. So that's how we get the VTH. So eventually the circuit that we need, which will require this VTH here, so we have now the VTH equaling to 4.2 volts. Now let's find out the RTH. So we still have our circuit here, and all we need to find is all we need to find out is the RTH. So we want to find out the resistance across this part. So what do we do to find the resistance? To find RTH, this is the key thing that we need to know. To find RTH, to find Thevenin's resistance, that is remove. The key word is remove all sources. Removing all sources means, when we say all sources, it means voltage sources and current sources from the circuit. And so once we remove everything, you remain with only resistances, and then those resistances you find the total resistance. The moment you have the total resistance, then everything becomes very easy. So remove all the sources. So our circuit, which was having the current source, for the current source here, it had the circuit had the current source here of 21 milliamperes, then had the resistance here of 0.8 kilo ohms. Then the load, remember the load, we removed it long time ago to remain with this part here. And then we have this other resistor here, which is the 3 kilo ohms. And then we have finally this other one here, 2 kilo ohms. And the voltage source, which is here, this voltage source, and then so I can just extend a little bit of this here, just to make sure that things are almost looking alike. Okay, so we are told that in order to find the resistance across AB here, which is now known as the Thevenin's resistance, RTH, then we have to eliminate the sources. To eliminate a current source, we remove it. We disconnect it from the circuit. So I've removed the current source. It's gone. And once you have removed the current source, then now we can figure out the also. So this one we short circuit. We put a wire here and another wire here, so we current is easily, but we do that by removing it. So that wire, what it does is actually to remove it. So this is what we remain with here. And so we should be able to find the total resistance of this remaining circuit here, which is a piece of cake. The moment we have this now, this step becomes very easy. These two resistances here are in parallel, and once they are in parallel, their total would be now, in order to find out what is between A and B, would be in series with this other resistance here. And so once we do that, everything becomes very easy. So this is what happens. We have these two in parallel, and if they are in parallel, then we have the 2K in parallel with the 3K. So this would be the same as 2 times, they are only 2, so this is 2 by 3 over 2 plus 3. The phenomenon of product over sum. So this would be equal to 6 over 5. And then this 6 over 5 here, the resultant here, the resultant is becoming, we are getting here the resultant being 6 over 5 K. 6 over 5 kilo ohms. It's K because here you are having K for this times K for this, and here you are having K plus K, so it's only 1 K here which goes, the other K remains. So that's why we end up with, otherwise if you don't visualize it, you may think that the kilos will go, the kilo ohm will go up and down, and you end up having problems. So we no longer have anything in parallel. Now the 6 over 5 and the 0.8 are now in series. So 6 over 5, if you can use your calculator, 6 over 5 would give you 1.2. So this is the same as 1.2 kilo ohms. And now this 1.2 and 0.8 are in series, therefore RTH, this one here, would be the same, because now we want what is the total resistance in this circuit here. So this would be the same as 0.8 plus 1.2, and this is kilo kilo ohms, and therefore RTH should be implied. So therefore RTH, Thevenin's resistance, will be the same as 2 kilo ohms. Is it the case? Yes, 2 kilo ohms. So here we removed all the sources, the voltage and current source, in order to find the RTH, and this RTH is equal to 2 kilo ohms. So we have moved a long way to the promised land. Promised land is the moment we got RTH and VTH, then we have the Thevenin's equivalent circuit from which we can find the current. So that current which was at that point AB, I4, is the same as the VTH over RTH plus the load. Which load was is the resistance that is connected across that section. So now we have a VTH here, which is 4.2 volts, and then we have an RTH, which is the 2 kilo ohms, and then we have our 2-point output, and this output is the RL, and in the circuit which we have the whose value we want, the RTH is 0.1, the RL is 0.1 kilo ohms. And so the current across this part here, when you revisit the circuit, the current that would be flowing here, current I4, will be equal to VTH over RTH plus RL, which would be the same as the VTH 4.2 over the 2 plus 0.1, which is equal to 4.2 over 2.1, which is equal to 2. Therefore, the current I4 is equal to 2, and because we have volts, and down here we have 2 kilo, 0.1 kilo, so we have a kilo down, and so this would be the same as maybe amperes. And this is how we use Thevenin's theorem to find the current that was flowing in that whole circuit, in the circuit that we were given at the beginning. So in summary, is that you have to first find in summary, you need to find the voltage across the resistance that they have identified as that resistance where they say find to find the current through is you baptize it to the load, then remove it and keep it on the side because you're gonna bring it here. So once you keep it aside, then you work on getting the RTH, getting the VTH, And then once you bring it here, you take the loop here, this loop in here, and then find the current I4 using this expression. I hope you have got something out of this. Try finding the same current using the superposition principle, that is isolating the current source out or taking the voltage source out. You get the current, take the current source out, get the current and add the two, use the Norton theorem, and see also whether you get the same answer at the end of the day. I will be doing this, we shall get another example and do it step by step and see whether we can get understanding of these principles, which sometimes look a little bit complex. Thank you for visiting. Remember to subscribe and turn on notifications, and hopefully we shall be doing, or we shall keep together on this journey. Thank you so much.